Welcome to the debate. Our focus today dives right into the heart of magnetic resonance imaging, the physics and, well, the practical implementation of K-space trajectory creation. We all understand that MR imaging fundamentally relies on encoding spatial information into a frequency domain, K-space, using these controlled magnetic field gradients.
Right, and that control is absolutely key. It's, the foundational physics. The position we trace in K-space, it's determined by integrating the strength and duration of those applied magnetic gradients over time. So what that means is the path is entirely determined by the waveform we actually feed the gradient coils. The receiver then just, records the MR signal, which mathematically is the value of the Fourier transform of the object's spin density taken along that specific path.
Precisely. We have, in theory, total control over the physical encoding mechanism. But that control runs straight into two pretty immutable limits: the inherent short lifespan of the MR signal, what we often call the tyranny of time, and the physical limitations of the gradient hardware, specifically how fast we can turn the gradients on and off, the slew rate. So this brings us to our central disagreement today. To get fast, high-quality images, should MRI acquisitions stick with these highly structured, predictable, fixed classical trajectories, or should we be moving toward dynamically learned and optimized trajectories?
Yeah, I'm firmly on the side of dynamism here. Given those hard limitations you just mentioned, I think we have an obligation, really, to maximize data collection efficiency. I'd argue that these fixed, sort of historical patterns are inherently inefficient precisely because they ignore the context of that transient signal. Adopting dynamically optimized, learned trajectories, often leveraging pretty advanced tools like neural ordinary differential equations or nodes, is, I think, the essential path forward for accelerating MRI acquisition without just throwing away quality.
I see why you favor optimization, but I think you sacrifice a degree of certainty for that efficiency. I support sticking with the fixed, structured trajectories, chief among them the Cartesian grid used in Fourier transform imaging, but also, established radial and simple spiral patterns. The undeniable strength of this classical approach lies in its mathematical guarantee. You get simple reconstruction via the fast Fourier transform, the FFT, and crucially, highly predictable artifact behavior. When you need reliability in a clinical setting, certainty often matters more than maybe fractional improvements in speed.
Certainty is admirable, I agree, but it doesn't stop the clock, does it? The fundamental problem is that we are mapping a landscape that is, actively dissolving while we're trying to map it. After that RF excitation pulse, the signal decays exponentially based on the R2 relaxation time. So sticking to a rigid, fixed pattern means we inevitably spend precious acquisition time traversing K-space locations inefficiently, especially as the signal strength just plummets. The learned approach, on the other hand, it recognizes this transience and optimizes the path in real time, essentially, to prioritize the most critical data points while the signal is still strong.
But that very rigidity guarantees spatial accuracy. We know, based on, basic Nyquist principles, that the desired spatial resolution is directly determined by the maximum extent of K-space we sample. And the field of view is dictated precisely by the K-space sampling interval, the delta K. We can write the pulse sequence, and we know exactly what image quality metrics we are going to achieve. And, importantly, we have powerful physical methods to fight that tyranny of time within that rigid framework.
Okay, let's talk about that rigidity, though, specifically in the context of acceleration. Because when clinicians push for faster scans, they inherently have to undersample the K-space grid. Now, when you undersample a fixed Cartesian grid, you introduce pretty severe structural artifacts and aliasing, and that requires massive post-processing fixes, things like parallel imaging or compressed sensing, just to compensate. That seems like complexity born out of necessity, not really by design.
I would argue, though, that those fixes are well-vetted, established clinical tools. They work.
They work, sure, but the dynamic approach minimizes the initial error. By treating K-space acquisition as this dynamic optimization problem solved by, let's say, a neural ODE, which conceptually is really just AI learning the absolute fastest and most efficient way to navigate the physical constraints, we condition the trajectory to inherently minimize structural artifacts from the get-go. The resulting paths, they achieve a fundamentally more balanced and uniform sampling density distribution across the whole of K-space. And what that means is the resulting point spread function, the PSF, has significantly reduced side lobes. So we're solving the artifact problem more in the acquisition domain, not just pushing it down the line to reconstruction.
That's a powerful claim, but let's maybe pivot for a second from data acquisition efficiency to the practicalities of image recovery. Your dynamically optimized path might yield a theoretically beautiful sampling density, sure, but if you actually look at those learned trajectories, those wavy, nonlinear, sometimes seemingly arbitrary paths, you see an immediate practical problem. For fixed Cartesian sampling, reconstruction is direct, it's fast, and it uses the universally available fast Fourier transform.
And your point is?
Instead, we're forced into mathematically intensive methods like the non-uniform fast Fourier transform, the NUF-FT, or maybe other specialized algorithms. This significantly increases the computational burden on the scanner's processing unit, right? It introduces delays and potential sources of error in the reconstruction step itself. In a high-throughput clinical environment, that trade-off, it's often prohibitive. You might gain speed in acquisition, only to lose it and maybe more during reconstruction.
Okay, but that reliance on the speed of the FFT, that's really a historical constraint, right? Not a fundamental scientific limit. It reflects the computational power we had back in the, 1980s?
I agree that today's clinical sites often lag behind the cutting edge, but the technology is moving quickly. We're now seeing real-time reconstruction devices using massive parallel processing hardware, like large arrays of simple, efficient processors, FPGAs, for example. As long as we precisely record where in case space we sampled the data, which, let's be clear, we have to do anyway, regardless of the path, the image can be built in real time. This makes the need for a simple, structured path kind of obsolete, doesn't it? Complexity in the path doesn't necessitate slowness in reconstruction anymore. I'm not quite convinced at that line of reasoning. Upgrading every single scanner in the field to support custom, high-speed parallel NFI, that's a monumental logistical hurdle, not to mention regulatory.
Let's maybe set aside the hardware arguments for a moment and return to the fundamental physics of decay. Because I think this is where the classical approach truly shines. The spin echo sequence, using that physical 180-degree inversion RF pulse, it's an elegant solution precisely because it actively reverses the phase defocusing effects caused by static field inhomogeneity.
It's physically elegant, yes, I grant you that. It is more than elegant. It's robust. It preserves signal intensity for a much longer period, allowing for stable, high-quality multi-shot acquisitions without those severe decay artifacts like ghosting or blurring that you get from asymmetric apodization. This physical mechanism offers a dependable, predictable signal extension that no arbitrary gradient waveform can just replicate on its own. It addresses the R2 problem right at the source.
I agree that physical refocusing is a powerful tool, but that elegance comes at a pretty severe cost: time. The spin echo sequence inherently demands a longer repetition time, the TR, and that drastically limits the overall scanning speed. Dynamic trajectory optimization, on the other hand, it fights the tyranny of time in a more subtle, perhaps less costly way. Since the learned trajectory prioritizes speed, remember, the velocity of K-space traversal is proportional to the gradient strength. It ensures we spend minimal time acquiring that vital central K-space data, where the signal is strongest. But beyond just the efficiency of the path, we can also utilize simple numeric correction. We don't necessarily need a physical pulse to correct for decay. We can simply log the precise time of acquisition t for every single data point read by the receiver. Then, we can digitally recover the true signal value using that formula, Q of k equals Q of k times exponent R2 times t. We're mathematically boosting the faint signal back to where it theoretically should have been.
Okay, but that exponential correction is, I think, fundamentally dangerous, and this is where clinical reliability could really break down. While this technique can, yes, theoretically extend the useful time window maybe by a factor of 2 or 3, that recovery comes at a serious price. You are multiplying your raw signal by an exponentially growing factor. As time t increases, that correction factor skyrockets. You are not just boosting the MR signal, you are exponentially amplifying all the background terminal receiver noise that was acquired at that later time point as well. This exponential noise amplification inevitably, I would argue, degrades the signal-to-noise ratio potentially to clinically unacceptable levels, making the images unusable long before the actual R2 signal has truly vanished. We need robust methods for clinical diagnosis, not.
That's a fair assessment of the signal-to-noise trade-off. I'll concede that, but it must be optimized against the specific image application we're talking about. If we look at the raw time savings achieved where this kind of numeric correction might allow for, say, a near 10-fold reduction in overall scanning time needed for a certain quality of volume, the clinical gain is potentially immense. We are balancing acceptable noise levels against dramatically reduced scan times, which improves throughput and, importantly, patient comfort.
Scan time reduction is irrelevant if the resulting waveform, violates the laws of physics or the limits of the hardware. Let's talk about those hardware constraints. The k-space path must always start at the origin, k0 equals 0. If an unconstrained learned trajectory demands really abrupt turns, sharp corners, it's going to violate the gradient slew rate limit, the S max. The classical paths, the straight lines in radial sampling, or the smooth zigzags in Cartesian, they are successful partly because they are easy on the gradient amplifiers. They ensure physical feasibility and, critically, reliable reproducibility across different scanners, different manufacturers. How can we trust a dynamically learned path that might be pushing the hardware right to its absolute physical limits?
Well, we eliminate that risk by making the optimization physics-informed from the start. When we train the neural network, or whatever optimization framework we're using, to find the optimal trajectory, we explicitly condition it on the real-world MRI hardware constraints. We enforce that the traversal velocity is limited by the maximum gradient amplitude, Gmax, and that the acceleration, which dictates the slew rate, is limited by the maximum slew rate, Smax. The result is a physically feasible, hardware-friendly waveform. And furthermore, these trajectories aren't just globally fixed, they are context-aware. There are studies showing that a trajectory optimized for the, let's say, centralized k-space features of a brain scan looks fundamentally different from one optimized for the more scattered k-space features you might see in a knee scan. This, to me, proves the dynamic method characterizes the inherent image features better than any rigid, globally fixed pattern could ever hope to.
Context awareness is interesting, I'll give you that, but standardization is absolutely vital in medicine. Ultimately, the reliable recovery of the final image back in our space, it relies on standardized Fourier principles and clear sampling criteria, like the Nyquist theorem. Deviating from these structured grids sacrifices the predictable, well-defined image quality necessary for clinical robustness. Think about it. When an image artifact appears, and they always do eventually, a technician needs to know exactly what type of decay or asymmetry or undersampling pattern caused it, and they need a standardized procedure to correct it, maybe rotating the charting pattern or adjusting timing parameters. Your learned path, while potentially efficient, introduces what is effectively an optimization black box right into the encoding mechanism. That makes clinical diagnosis and, more importantly, correction of artifacts infinitely harder.
The black box argument, I think that's only a transitional phase. As these optimized methods become better understood and standardized themselves, the efficiency gain is just too significant to ignore. The future of rapid MRI, it demands that we intelligently maximize the data collected within that incredibly short, transient lifetime of the MR signal. By framing the k-space path, KFT, as a collaborative optimization problem, working with both the hardware limits and advanced reconstruction networks, we move past the historical constraints of rigid sampling methods that were designed primarily for, let's face it, computational simplicity decades ago. The highest quality image achieved in the shortest possible time, that has to be the superior design principle moving forward.
Well, we both certainly share the same goal, maximizing image quality and speed, using gradient fields to encode spatial frequency information into k-space. The fundamental debate, however, it seems remains open. Is stability derived from classical, simple implementation and physical compensation the true path to long-term clinical success? Or does the maximal efficiency derived from flexible, learned optimization offer the necessary leap forward for next-generation MRI?
I think listeners will probably recognize that the time for purely simple implementation might be ending. The future seems to require intelligent adaptation to the physical reality of the MR signal itself.